Now, we have done this whole construction of inverse functions on the assumptions that they exist, but do they? Well, let's think about it. Let's start by refreshing our memory on what a function is, right? Not every relationship between two variables is a function. In order for us to have a function, we must be dealing with a relationship that passes the vertical line test. Okay, what does that mean? Well, let's say that I'm claiming this is the graph of a function. Well, that means that for each x, there is only one value of y corresponding to it. So this is called the vertical line test because it can be done by drawing a vertical line and sort of scanning the whole curve through this vertical line and making sure that this vertical line hits the curve at most in one point. It's okay if it doesn't hit it at all, as it is right now, but it cannot hit it more than once. So for instance, if I look at this curve, that is definitely not a function, because if I try to run the vertical line test, you'll see right away that this line is going to hit the curve in 2 points for many values of x. Alright, so let's go back to our original function. In order for this function to have an inverse, the inverse has to be a function. So the inverse has to have the same property, but with x and y reversed. So that means that for each y, we can only have one x in the original function. So that means that now I'm going to draw a horizontal line and scan the curve with it and make sure that this horizontal line will cut the curve or at most at one point. Maybe not at all, but the important thing is it does not cut it more than once. And for obvious reasons, this is something called the horizontal line test. Notice, for instance, that as we try to apply these tests to this familiar parabola or parabola-looking curve, we're not sure it is a parabola, but it looks like one. Well, the vertical line test works fine. If I draw a vertical line and I use it to scan my curve, it cuts the curve at most in one point. Again, it may not cut it at all, but it does not cut it in more than one point. However, if I run the horizontal line test, then the parabola gets cut twice by this horizontal line. So that means that this is a function, but it does not have an inverse. Okay, so going back to our original example, we're going to say that a function that does have an inverse is the invertible, or 1 to 1. 1 to 1 meaning that for each x value there is only one value, y value, and for each y value there is only one x value. Now, there are some situations where we're dealing with functions which are not invertible, and yet we would like to make them invertible. Well, there is a way. Okay, so a function that is not invertible, like our good old parabola here, can in fact be made invertible. How do we do it? Well, with some magic. Not really. What we're going to do is we're going to ask ourselves, well, what is the problem? Why is this thing not invertible? Well, because it doesn't pass the horizontal line test. A horizontal line will cut this parabola in more than one point. Well, what we can do is we can restrict the domain of this function so that each horizontal line will only cut it in one point. So in other words, we're going to throw away a chunk of the function. So for instance, what we can do is we can throw away all that left side and therefore use as domain only x greater than or equal to 0. Well, if we do that, now we've got a function which is in fact invertible. Now we can run the horizontal line test and it works. Okay? So this is the standard way of making a function invertible, and even though it may look like a bit of cheating, but it does have many useful applications, and in fact we will use this particular trick many times. So we have seen how to identify whether a function has an inverse if it is invertible, but assuming it is, how are we going to figure out what its inverse is? Well, there are actually two ways in which we can do that if possible. That means that there are some functions for which neither one of the two methods I'm about to explain will actually work. But for now we're going to think positive and assume that these methods do work in the function with the function that we're dealing with. So let's say the function is f of x. In the first method, we're first going to switch x and y names. Remember, this is the essence of inverse functions. We're switching the roles of x and y. So from y equals f of x, we're going to change that to x equal f of y. We're just changing the names, and we're not changing the formula. And then from there, we're going to solve the corresponding equation for y. So this is going to give us y equal, well, whatever relationship we come up with is got to be the inverse function of f. Or we can switch those two steps. The second method is first we solve for x. So we start from y equals f of x. So we're going to figure out how to solve for x, and therefore x is going to be the inverse function of y. Remember the whole point of the inverse function, we want to go back from y to x. But at this stage now we want to switch the names because we want to maintain our good old standard notation. And so we're going to switch x and y. And so again we're going to end up with the same thing, y equals f inverse of x. As I said, this procedure doesn't always work, and so sometimes it's impossible, and in that situation we may have to simply devise a different name for this new function. Let me give you a few examples of how that works. Here's the first example, or transformation that changes Celsius temperatures to Fahrenheit. So we're writing it down just as a pure mathematical function. Now remember, f of x is actually our y variable. So let's use both of the techniques. So the first technique is, first of all, we're going to switch x and y. If we do that, our relationship becomes now x equal 5/9 of y plus 32. Then we're going to solve for y, and I trust you know how to do that, and in fact I invite you to do that on your own, and make sure that you end up with this relationship, 9/5 of x minus 32 equals y. Okay? Or we can use the other method. We can solve first for x, and so we're going to end up with 9/5 of y minus 32 equals x. And then from there, what we can do is we can switch x and y, and of course we come up with exactly the same relationship. Now, yes, this relationship is a bit backwards in the way it's written. I'm writing something equal y instead of y equals something, but this is the stage where we're going to clean up the notation and write that f inverse of x is 9/5 of x minus 32. Remember that I told you not to confuse the inverse with the reciprocal. For instance, notice that in this case, the reciprocal of our original function, f of x to the negative 1, is 1 over 5/9 of x plus 32, which is a far cry from the f inverse of x, which is still a linear function. Let's have a look at another example. Well, this time let's look at the function x cubed minus 4. Once again, g of x is going to be equal to y. And we can either switch first, in which case we end up with x equal y cubed minus 4, and then solve for y, which gives us cube root of x plus 4. Or what we can do is we can solve for x first, that gives us x equal cube root of y plus 4, and then switch x and y, which gives us exactly the same thing. Going faster now, you may want to slow down and on your own make sure that you can do the algebra involved here. Either way, we are going to end up with this inverse, g inverse of x equal cube root of x plus 4. Notice again, in this case, g of x has nothing to do with the g that I used at the beginning of this lecture to denote the inverse. That was an initial notation which we're not going to use anymore. G of x is just a new function. Also, notice that once again, this is not to be confused with the reciprocal. G of x to the negative 1 is 1 over x cubed minus 4. Again, very different from this one. Here is another example which is a little bit more interesting. So let's look at that parabola, x squared minus 3, and now I know it is a parabola because the formula is that of a parabola. And now I would like to get the inverse for this function. Well, I know I can't do that because this function is not invertible. So we need to restrict the domain, and we're going to do that exactly as we did before. So what we're going to do is we're going to restrict it to x greater than or equal to 0, which throws away the whole left-hand side of the curve. So we're going to just invert the right side of that function. Now at this point, what we're going to do is follow exactly the same algebraic steps as before, which means we're going to let y equals x squared minus 3. Then we're going to solve for x, and we're going to take the square root. Oops, now we have a problem. Because in taking away the square from x squared, well, that's not quite the same as taking the square root, is it? Taking away the square means that we have to consider both the positive and the negative square root of y plus 3. But we can't have that because we need a function. We cannot have that kind of indecision. It has to be either plus or minus. And this is where we're going to look back at our domain restriction. Remember, we decided we were going to use only x positives, or at least 0. And so what that means is that our choice has to be for the positive square root, which means we can simply delete the plus or minus and be left with the square root. We're not done yet because of course we need to still switch x and y, but that's easy to do, and therefore the inverse of our original function is the square root of x plus 3. To look at the graph of this inverse function, all we have to do is reflect it in our mind across the line y equals x, and when we do that we obtain this shape. Notice once again that what we have obtained is not the reciprocal. The reciprocal is something else, is 1 over x squared minus 3, and you may want to check on your calculator what the graph of that function looks like. Definitely not like the blue curve you have in front of you. And we're going to finish with something a little bit more challenging. So let's look at f of x equals sine x. Now that's the familiar wavy curve that is associated with sine x, and that's obviously not invertible. It's very not invertible. Every horizontal line will hit either not at all or in infinitely many points. Well, in many applications we still need to reverse that function for a number of reasons. But we can't do it the way it is now. We can, however, do it by restricting the domain. Well, we have lots of choices here for how to restrict the domain, but usually we go always for the simplest one, the biggest one and the simplest one. So we're going to look at the largest chunk that we can use around 0 so that the horizontal line test is okay. And that means, of course, restricting our function to the interval negative pi over 2 to pi over 2. Because as you go below negative pi over 2, the function will start going up again. And if we go beyond positive pi over 2, the function will start going down again, and we'll lose the horizontal line test. Well, now that's become a pretty small chunk, so we better have a better look at it. We'll zoom in and look at the same curve, the same restriction, but slightly bigger view. Now the problem is that we cannot solve for x, right? I mean, how are we going to get the x out of there? Sine x does not have a formula, and therefore we cannot possibly solve for x. And yet this function clearly has, with this restriction, clearly has an inverse. In fact, I can even draw it. Okay, all I have to do is draw the line y equals x, reflect my original curve around this line, and end up with the blue curve, which is the inverse. But how are we going to denote this inverse? Well, the only way in which we can actually obtain this inverse is by giving it a new name. In this particular case, this new function is something that we're going to call the arc sine of x. Okay, or some people denote it simply as sine to negative 1 of x, but remember that negative 1 is attached to the name of the function. It represents the inverse, not the reciprocal. I'm going to come back to that in a second. Also, you're going to find on some calculators that it is also denoted by a sine x. So either one of these names, but basically it's a new function and we don't have a formula for it. All we know is that it is the inverse function of sine x, and this is something that we're going to have to do in more than one situation. And again, as I just said, notice that this function is not the same thing as f of x to the negative 1, which is 1 over sine x. Do you remember what 1 over sine x is? Well, it's something called the cosecant of x. And if you check its graph on the calculator, again, is very different from the blue curve that we have constructed so far. So here are some examples, work on some more, and then we're going to see this concept of inverse functions applied in a whole bunch of other situations.